Hello, we're going to talk about another 2D NMR experiment. It's called an inadequate. It's also a homonuclear correlation experiment, like a COSY, but it measures the one bond carbon carbon correlations. So we have an example up here. We'll go through a couple of them and we'll talk about some of the issues with it. So this is ethyl benzene. And if we look at the correlations here, this is carbon one is the methyl, and this is beautiful. This line here, oops, can't draw a straight line. This line shows you that this is connected to carbon two. And then you can drop down, dot, 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 because this is also carbon two. It's a peak showing up under carbon two. And you just slide over, and it's connected to carbon three at 140 something. And then you drop down, and whatever is aligned with it is bonded to it. So 3 is bonded to 4, and then you can go up and see that 4 is bonded to 5 and 6. And this 4 to 5 maybe, so here's 3 to 4. 4 to 5 is a tiny, but then we go on up 5 to 6, and those are all the carbons in the molecule. So this can be very powerful because it just walks you down carbon, 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 carbon. But, exclamation point, attention. Um, this could be very useful, but carbon 13 is not very abundant. Whenever you get a sample of carbon, only 1% of it is carbon 13. So the rest is carbon 12, which doesn't show up, which means that the odds of finding a carbon 13 next to another carbon 13 is almost impossible. I mean, it's not even right. It's much, much less than 1%. So it's very unlikely. And because of this, you might scan for days and you need large quantities or many scans. The other alternative is you could use an enriched sample. So if you had carbon 13 and you were able to feed it into an E. coli and have it incorporated or synthesize your molecule when enriched with carbon 13, then this could be much more useful. But you are limited by the fact that by the sensitivity and the abundance. Um, so we'll just look at one more example though. And so I've numbered the carbons here. We know we have C8H18. So the first thing you should always do is calculate the sites of unsaturation. That would be 8 times 2 is 16 plus 2 is 18. So there are no sites of unsaturation in this. So there are no double bonds or rings. If I look, I've got 8 carbons. That fits, so I have no symmetry. I have something at 65, so that's got to be bonded to my oxygen. So this is my CO. And I can look, and 1 is only bonded to one other carbon. So I'm going to guess right away that this is my oxygen and it's bonded to carbon 1. And then I can just walk myself down the chain here. 2 is bonded to 3. 3 is bonded to 4. Oh, but here we have 2 is also bonded to 7. So if we go over here, we have carbon 2 and it's bonded to carbon 7 and it's bonded to carbon 3. Did I do that right? No. Ah, okay. So, I need a ruler, don't I? Yes, so let's start over. So if this is 1 and this is 2, I apparently can't draw a straight line. So there's 2 bonded to, here we go, 6. 6 is bonded to, oh, it's hard to tell between 4 and 5. It looks like it's 4 to me. And then 4 is bonded to 5. 5 is bonded to 3. There we go. 3 is bonded to 7, and 7 is bonded to 8. So we can walk them down. Let's get rid of this, huh? And this is HO bonded to C1, bonded to C2, right? 2, 6, 6 bonded to, we decided 4, which was to 5, and then 5 was bonded to 3, and 3 is bonded to 7, and 7 was bonded to 8. There we go. So this looks like it's octanol. And just make sure you draw your lines straight. It's often better if you've got this on paper, which you do, to use a ruler. Okay, so do a few practice on these and they're pretty straightforward.